Awesome.
Yep.
Life is hard because it gives you the test first, then the lesson. I don't actually know who said that. So today we're covering the E6B. Somebody reached out and asked specific questions about that. We're going to cover weather and airspace. I will post this here so you guys can... Sorry, but give me a second. I'll post this so you guys can see. You can practice along with me. Okay, so you should be able to follow along with me while I do all the calculations and stuff. So let's just get into it. We'll start with an emergency procedure like we always do. We'll get into this week's questions. There's some great questions that came out this week. We'll go into the overview of the E6B. We'll get into weather and airspace, and of course, a Q&A. I'd like you guys to follow along with the E6B. It's going to be really, really beneficial for you guys to get that practice in. Okay, cool. So first, the first question was our search and rescue brief. So this week's homework for next week, which is the last meeting I believe we have scheduled, you guys are going to present a flight brief essentially. And what I'd like that to be is to follow the Northwest Craft checklist to start off. So that's NOTAMs, weather, known delays, runways, alternates, fuel, and takeoff and landing distance calculations. So when you go to the course, there should be a PDF document that gives you a mission brief, and I want you to use all the knowledge that you've acquired through the course and apply it. Basically, create a flight plan and then be prepared to defend it. This is going to mirror very much your check ride. When you go to your check ride, your designated pilot examiner is going to give you a flight, let's say from Bellingham to Hoquiam, and he's going to want to see what route you choose, how you get there, and then what altitude you're going to pick, and then basically what your reasoning is behind the flight. And he's going to just grill you about it. He'll be like, all right, what are the NOTAMs for this flight? Why did you choose this route? Who do you expect to talk to? And he's just going to basically take an hour and just grill you about your flight, right? It's kind of like defending your doctoral dissertation. That's kind of how I think about it. If you have any questions, any further questions about the search and rescue brief that I have assigned, just go ahead and reach out to me and I can help you out individually. And then next week, it's pretty much just going to be you guys sharing what you have planned. If you are comfortable with it. Of course, if nobody volunteers to do it, this is not a paid course, so it's completely voluntary. If you're like, this is stupid, I don't want to do it, that's fine. But I think it's a really fun practice brief. Oh, also, the ground reference maneuvers that you're going to be using for your search pattern, I want you to either talk about turns around a point, as turns across the road, or the rectangular course, or you might even use more advanced ground reference maneuvers to conduct your search. You can use your imagination and come up with, whatever you got. I will be asking you questions, so be prepared to answer questions about like airspace or, your Part 91.103 checklist, that kind of stuff. Any questions about that? No? Great. And again, if you do have questions throughout the week, or if you'd rather just do it one-on-one with me, that's cool too. I'm totally happy to schedule a one-on-one call with you guys if you'd rather talk about your brief that way. The second question I got this week was about our flight program that I'm trying to start up mid-January. Basically, it's going to be in 4 phases. Phase 1 is going to be airplane familiarization. We're going to go up in the aircraft and just get you comfortable talking on the radios, doing the basic maneuvers. It's really just an aircraft fam. Phase 2 is pre-solo. You are going to be drilling emergency procedures, radio communications, the traffic pattern, ground reference maneuvers, that kind of stuff. And we're just going to get you ready for your first solo. That's going to culminate with your first solo, 3 trips around the traffic pattern. And then once you've got that, we're going to cut your shirt, take some cool pictures. And then phase 3 is going to start. We're going to do cross-country flight planning. You're going to go up and do longer flights, like 50 nautical miles or more. Anything greater than 50 miles will count. And then phase 4 is really just check ride prep. We're going to be just, getting you ready for the check ride, which will culminate in with the check ride or the practical exam, where you will go up against a DPE or a designated pilot examiner and show them what you know, and you're going to get your wings. And then we will have a great big party at the end of the course with everybody that sticks with it. My objective is to get it done in about 14 weeks. And we're going to prioritize students who are really, raring to go, who are really willing to put in the time and knock it out. And then if we have any slots left for, more casual students, that's fine too. But I'd really like to front load students who are like dedicated to, get it knocked out as systematically as possible. So that's our flight program starting up in January. One of the flight instructors we're going to have is almost a carbon copy of me. He's also an airborne ranger, who's also a pilot, who's also a mechanical engineer, who also went to UW, and he helped me start the flying club over at UW Bothell. So he's an awesome dude. I'm really excited for you guys to meet him. And that's kind of how the flight program is going to go. Questions about the flight program? No? Awesome. Let's get into our emergency procedures. Let's say we're flying along and you lose your engine. You notice your tachometer just drops down, your propeller stops spinning, and then it gets really, really quiet. What do you do? Give me a volunteer. And if I don't get one, I'll call somebody. All right, that's cool. Anson, what do you think? We lose our engine. What do we do?
Well, you would kill your engine, so just like shut it off.
Yeah, kind of. Yeah, so
your glide angle,
right?
I mean, you'd try to restart your engine. So you have, like, if that doesn't work, then you would trim for the best glide angle and look around for a place to land.
Yeah, so remember the ABCs of an engine failure. A, B, C. A is airspeed. Pitch for your best glide speed, and this aircraft is 65 knots. So you're going to manipulate the flight controls and trim off control pressures so that your airspeed stays stable at 65 knots. B, best place to land. Before we start trying to restart the engine, we're going to look around and find a field or airport that we're going to land at and put our nose towards that field. And then C, finally, we'll run through our checklist. Then we can use a flow to try to get the aircraft back online. Maybe we bump the mix or pull the mix accidentally, put the mix back in, try to restart it. And then if that doesn't work, the next steps are D and E. D, declare an emergency, talk to whoever you're talking to, tower, air traffic control, flight following, whoever, and just say, Cessna 2 Sierra Papa is declaring an emergency. And then E, execute your forced landing. And that's also a checklist that you can do. But basically, you're just going to transition to slow flight right over the field or runway. And remember to sacrifice the aircraft. The aircraft is not alive. We don't care about the aircraft at this point. You can use whatever you need to keep you and your passengers alive. Cool. So there's that. Let's say we have a vacuum failure in our aircraft. What instruments are you likely to lose? How about Bobby? Bobby, what instruments do we lose if we lose our vacuum?
Is it any of the ones with the system?
This is going to be the vacuum system. Do you remember which those are? That's okay if you don't. I'll talk through them. So these three here are your pitot-static instruments, right? They are governed by air pressure, which is the pitot-static port, the static port and the pitot tube. Pitot tube gives you ram air pressure for the airspeed indicator. The altimeter and the vertical speed indicator take static air. This guy here is electrically driven. It's a gyroscope, but it's an electrically driven gyroscope. And then these two are our vacuum-driven gyroscopes. So if we lose our vacuum system, which is engine driven, we're going to lose these two gyros. So this will probably drift off into some weird angle, and this will indicate some incorrect heading. So if you see your vacuum drop off, there's a very good chance you're going to lose attitude and heading information. And if you're VFR, it's not a huge deal. You still got your compass up here, and you've got the planet as your attitude indicator. But if you're in IFR conditions, then you're going to have to revert to your compass heavily, and then your other instruments here, which are going to give you pitch and bank information. Cool. That's two emergency procedures. You guys are on top of it. Stick with it. Practice it. Go study emergency procedures in your pilot operating handbook. It'll make things a lot easier. Let's move on to the E6B. The E6B is essentially a slide rule. There are two sides to it. There's the wind component side, and then there's the flight computer side. They're basically, again, a slide rule. The rectangular portion here on the flip side often has additional reference material that can be pretty useful. So, go study it. Now, the circular side allows us to solve a variety of problems, including time, speed, distance, and fuel consumption. Essentially, we're going to use it to establish ratios. That's really what it comes down to. And I'm going to switch to the E6B simulator so you guys can follow along with me while we do these problems. Okay, can you guys still see my screen okay? You got the E6B on the right side and the PowerPoint on the left side. I'm going to assume yes. If not, let me know. So the first step is always finding our something per hour for most problems. In this case, we are looking for speed, 150 knots or 150 nautical miles per hour, and we've flown for 35 minutes. Now we need to figure out how far we have gone. Make sense? So speed 150 knots, we're going to find on the outer scale is our distance values. On the inner circle part is our time value. So we're going to find 150, in this case 15, and we're just going to add on a 0 to it mentally. And we're going to line up these two lines, 150 nautical miles per hour, and we're going to go to 35 minutes on the time side. And we're looking for 35 minutes right here. And we want to be careful. We're not looking at this arrow here. Don't get confused. This arrow has nothing to do with this 35 here. This 35 has its own little corresponding line. So we look up here and read the 80, 85, 86, 87 nautical miles that we have flown in 35 minutes. Does that make sense? How's this? If it doesn't make sense, let me know. Yeah, cool. Now let's do the second problem. Our speed is 120 nautical miles per hour, and we've flown for 45 minutes. So first, we're going to set our rate, 120 nautical miles per hour. And again, don't look at these arrows here. That's for something else completely different. So don't get confused. 120 nautical miles per hour. And we're going to look for 45 minutes. And it looks like we will have flown 90 nautical miles. And of course, you can always double check this with a regular old calculator if you're so inclined. Let's do a third one. Speed 90 knots, and we have flown for an hour and 40 minutes. And of course, I hope you guys are practicing this on your own. So let's set it. What is our rate? 90 nautical miles per hour. And we've flown for an hour and 40 minutes. And where's our hour and 40? Right here. Hour and 40 minutes. We've flown for about 150 miles-ish. Now let's flip it to a different set of problems. What's our endurance? How far can we fly given our certain parameters? In this case, we have 4.5 hours of fuel. We have 4.5 hours of fuel, and our ground speed is 125 knots. What do you guys think is our rate for this problem? Well, is it 4.5 hours, or is it a ground speed of 125 nautical miles per hour? It's 125 nautical miles per hour. So we go to our rate, 125 nautical miles per hour, and we've got 4.5 hours of fuel. So we're going to look for our 4 hours and 30 minutes. And it looks like we have a range of about 560 nautical miles. There's 550, 560, this is 600. Now, it can be a little confusing trying to figure out where to put the decimal place. And it just kind of you kind of have to think about like, all right, if I'm flying 4.5 hours at a greater than 100 knots, 4 hours, that's at least 400 miles and then some. So that's where you're going to put the decimal place, right? You're definitely not flying 55 miles after 4 hours of flying. Okay, why is this not? Here we go. All right, so let's do another one. 120 knots for 3 hours. 120 knots, 3 hours. And I apologize if this gets tedious. I know people don't like playing with the E6B very much. But for 3 hours at 120 knots, you're going to be flying for about 360 nautical miles. That's our range. So if we were to maintain this this ground speed for 3 hours straight, we could fly 360 nautical miles. And the last one, our ground speed of 110 knots and 6 hours of fuel. 110 knots here and 6 hours of fuel. We could fly for 660 nautical miles, roughly. Right between the 6 and 7, 660. Yeah. So that's our time, speed, and distance problems. If it doesn't make sense, let me know. How's that? There we go. Okay, now let's say you want to figure out what your ground speed is. You know you've flown a certain distance and a certain time. Now we need to figure out what our ground speed is. And remember that your airspeed isn't necessarily your ground speed. You could be indicating 120 knots, but if you've got a straight headwind of like 50 knots, your ground speed could be much slower than your airspeed. And that could also be the same for if you've got a tailwind. You could be indicating a very slow airspeed, but you could be hauling because the wind is pushing you. So let's figure out what our ground speed is. Given 26 nautical miles in 13 minutes, now what's our rate in this case? We really don't know. And that's the point. We're trying to find what our rate is. So for 13 minutes, we'll find 13 minutes on the minute side, 13 minutes and 26 nautical miles. And remember, it's not the arrow. This arrow has nothing to do with this 13 here. This 13's line is right between the 1 and the 3. And for 26 nautical miles, there's 24, there's 25. This should be 26 right here. What's our ground speed? Well, let's go look at our rate. 120 nautical miles per hour, give or take a few, right? Just about 120. Let's do another one. We've flown for 17 minutes straight, and we know we've flown for 30 nautical miles. So where's 17 here? 30 nautical miles there. And our rate is about 106 nautical miles per hour, or 106 knots ground speed. And the last one, 22 nautical miles in 12 minutes. Let's find the 12-minute dealio and 22 nautical miles. Right there. Right? And remember, it's not this arrow. It's the needle or the line right between the 1 and the 2. 22 nautical miles in 12 minutes is a ground speed of 110 knots. Bam. If it doesn't make sense, let me know. Cool. Let's talk about fuel consumption and endurance. We're going to set the fuel rate on the outer scale. Remember, this is something per hour, and we're going to read the amount of time we have on the inner scale. So basically, they're saying, hey, if you're going to burn 8.4 gallons every hour, and you've got 56 gallons sitting in your tank, how long can we fly for? If it doesn't make sense, let me know. 8.4 gallons per hour is our rate. 8.4 gallons per hour, right? And 56 gallons total comes out to about 6 hours and 40 minutes. 56 right here, 6 hours and 40 minutes, right? Now let's look at this one, 7.2 gallons per hour, 50 gallons total. So we've got 50 gallons sitting in our tank, and we know that our aircraft burns 7.2 gallons per hour. 7.5432, 7.2 gallons per hour, 50 gallons total. That comes out to 6 hours and 50 something minutes. 52 minutes maybe. Right? And then the last one, we have 45 gallons in our tank. We burn 6.5 gallons per hour. Let's see what we got. 6.5 gallons per hour and 45 gallons total. Again, that comes out to just about 6 hours and 50 minutes. I should have a different variety of problems. But if it doesn't make sense, let me know. That's how those work. Okay. Now let's talk about conversions. Another really neat thing you can do with these E6B flight computers is converting different values or different units. On the bottom scale here, we have our Fahrenheit to Celsius conversion scale. So if you're like, shoot, I have no idea what 20 degrees Celsius is. Well, it's right here. 20 degrees Celsius comes out to 68 degrees Fahrenheit. Or vice versa. If you're like, shoot, I don't know what 80 degrees Fahrenheit is. Well, that's 27 degrees Celsius. Right. So that's kind of neat. Real quick way to change from Fahrenheit to Celsius and back again. Let's say we need to change from nautical miles to statute miles. Nautical miles is here on this arrow where it says knot, and statute miles is here. So if we need to convert, let's say we want to go from 7 nautical miles, it's just over 8 statute miles. 7 nautical miles is just about 8 and some change statute miles. Let's say we want to convert kilometers to nautical miles. We're going to find the kilometer arrow. Let's say we want to go from 10 kilometers. Let's see how many nautical miles that is. That is about, 5.4 nautical miles? Is that right? Yeah, 5.4 nautical miles. Let's convert statute to kilometers. Statute miles to kilometers. Let's go 16 statute miles there. And then we go read kilometers is over here. Is that right? Did I right? No, I think I meant to say kilometers, 10 kilometers to statute miles. Is that right? Something like that. I'm screwing this up. My mistake. Statute 16. Yeah, there we go. It's 10 statute miles is 16 kilometers roughly. Right? And then fuel, gallons to pounds. If we want gallons, pounds are over here. So let's say we have 10 gallons, should come out to 60 pounds of fuel because that's 6 pounds per gallon. All right, so that kind of makes sense, I hope. Again, if it doesn't make sense, let me know. But that's generally how these conversions work. You just got to find which arrow corresponds to which unit, and then go find the other unit that you're looking for. And then just be aware, like, all right, does 1 gallon of fuel equal 600 pounds? Probably not. Kind of logic your way through your decimal places. All right, let's talk about true airspeed and density altitude. So let's refresh. What does density altitude mean? Density altitude is the altitude at which the aircraft feels that it is flying at. Things like temperature, pressure, and humidity are going to affect the performance of the aircraft. So a higher density altitude will degrade your performance, while a lower density altitude generally improves performance. So let's say you are given a pressure altitude, a temperature, and a calibrated airspeed. We want to find what true airspeed and density altitude we are at. So first, we're going to find by the way, the E6B actually gives it to you. Here's the how-to airspeed correction. Set your pressure altitude opposite temperature in the window, opposite calibrated airspeed on the inner scale, and read the true airspeed on the outer scale, and then read density altitude in the center. So if you just follow the instructions on the E6B, you're probably going to get it right. But again, it's the practice. It's the actually doing it that's going to make you proficient. So in this case, we've got a pressure altitude of 14,000 feet and a temperature of 5 degrees Celsius. Okay. Pressure altitude is in this window. Our temperature is on the outer scale of this little thing right here. So, and be careful, negative is to the right of 0, positive is to the left of 0. So 5 degrees Celsius at 14,000 feet. Here's 0, here's 5. And right here is 14,000 feet. Our density altitude is 16,000 feet. And our true airspeed, and I forget which one do I want to look at, calibrated airspeed on the inner scale, so 160. So our true airspeed is going to be 204, just about. Let's see. Yeah, 16,000 feet and 204 true airspeed. Nice. I got it right, believe it or not. Let's do another one, and you guys, again, follow along. I'll try to go a little slower. I know I tend to rush. Our pressure altitude is 20,000 feet. The temperature is negative 20 degrees Celsius, and we have a calibrated airspeed of 200 knots. What's our true airspeed, and what's our density altitude? Let's check it out. First, temperature, negative 20. Negatives are to the right of the 0. 20,000 feet. So this is 5, 10, 15, 20, and right there 20,000 feet, negative 20 degrees Celsius, density altitude of, what's that? Somewhere between the first tick mark. So if that's 25, this is going to be 21,000. Is that right? And then a calibrated airspeed of 200 knots comes out to 25, 26, 268. Is that right? Oh, no, I got that wrong. Hang on. 5, 6, 25, 26, 27. Oh, yeah, 273. My mistake. 27, and then 20,500, which is, yeah, makes sense. 20,500. All right, let's do one more. Pressure altitude of 8,000, 15 degrees Celsius. And remember, positive is on the left of the zero. So 15 degrees Celsius and 8,000 feet. 5, 10, 15 is this one. And 8,000 is about there. 0, 5, 10, 15. And that's 8. A little bit more. About there. And then calibrated airspeed of 150. And this is true airspeed of 174. And a density altitude of just under 10,000. Yeah, 174, just under 10,000. Not bad. Not bad. I got to be honest with you guys, we don't really do these very often, at least not the type of flying that I do. So it's nice to see that this stuff works. Now let's say we need to figure out what our true altitude is. Now this is an altitude correction. So we're going to use the other window over here. And again, it gives it to you on the E6B itself. Set your pressure altitude opposite your temperature in the window, opposite calibrated altitude on the inner scale, read true altitude on the outer scale. It can be a little tricky though. So here is the how-to. When the air is colder than standard, your altimeter may mislead you into thinking you are higher than actual. Again, this is because temperature affects what the airplane thinks you're flying at. So you're going to get your pressure altitude, air temperature. We're going to subtract the station elevation from the indicated altitude for calibrated AGL or absolute altitude. Absolute altitude. Then we're going to find the calibrated AGL on the middle scale and read the correction on the outer scale. Then we're going to add that correction to the station altitude to get your true altitude in MSL. And if your station is unknown, the altitude's unknown, we're just going to read the calibrated altitude and find the true altitude. So let's run through it. Again, we don't really do these very often, but you might find it on a knowledge exam. So it's worth practicing. So our pressure altitude of 10,500, indicated altitude of 10,000, temperature of negative 20, station altitude of 5,000. So let's start with our pressure altitude. 10,500 opposite negative 20 degrees Celsius. And here, our temperature is up here. Remember, the negatives are to the left of the zero this time. And our pressure altitude increases from right to left. So pressure altitude 10,500, negative 20. Just about there. 10,500 and negative 20 degrees Celsius. Now we're going to subtract our station altitude from our indicated altitude. So that's 5,000. And we're going to read that 5,000 here and find our correction, which is going to be 45, 46, 47, 475. So 4,750. Then we're going to add that to our station altitude. So 5,000 plus 4,750 comes out to 9,750, right? And then that should give us our true altitude, 9,750. Nice, there it is. Make sense? And again, if it doesn't, let me know. We're going to do a few more practice ones. I would like you guys to follow along if possible. Let's do it again. Pressure altitude this time is 12,000. Indicated altitude is 11,000. Negative 30 degrees Celsius. And our station altitude is 3,000 feet. So let's start with our E6B here. Pressure altitude 12,000, negative 30. 12,000 is here. And negative 30 is about there, right? Now let's subtract our station altitude from our indicated altitude. And that should be, I can do math. 11 minus 3 is 8,000. So we're going to find 8,000, and we've got a correction of 7,400-ish, maybe. And we're going to add that to our station altitude. So 3,000 plus 7,400 or so. Well, 10,400. Yeah, 10,350. Yeah, close enough. Bam. And so that's the true altitude. And what happens if we don't know our station altitude? Let's run through that one. Again, pressure, altitude, and temperature, -15. Pressure altitude is 8,000 here, and -15 is there. Our calibrated altitude or indicated altitude, 7,600. We're just going to read calibrated altitude or indicated altitude, 7,600 on the, and then find 600. It should be 7,200 or so. Yeah, 7,200. Look at that. Bam. Okay. So that kind of gives you an idea of what true altitude calculations look like. They can be a little annoying, but they're not that bad, right? I mean, you just run through the algorithm and you get it done. Now let's do some conversions. Let's say you need to figure out what your climb gradient or your descent rate needs to be. In this case, you know your ground speed because you use your E6B to figure out your ground speed. And now we need to figure out how fast we need to climb or descend. So first, we're going to set our ground speed for the first problem. We've got 120. We're going to read feet per mile on the middle scale and then read our feet per minute on the outer scale. So set our ground speed of 120 nautical miles per hour. That's our rate. Our feet per mile is 350. And so we need a climb gradient of 700 feet per minute. There it is, 700. Make sense? And again, if it doesn't, let me know. Let's do another one. Ground speed is 100. We need a descent rate of 250 feet per mile. And remember, now we're dialing in the professionalism as aviators. We need to have a specific climb or descent rate given our speed. So we need to figure out 100 nautical miles per hour, a descent of 250 feet per mile, and we need to descend at a rate of 415. Is that right? Yeah, 415 feet per minute. There we go. And the last one, 150 nautical miles per hour. That's our rate. About there. We need a climb gradient of 300 feet per mile. So we're going to climb at 750 feet per minute. Bam. So remember, our VSI, our vertical speed indicator, does not give us feet per mile. It gives us feet per minute. But when you go into the IFR world, a lot of your instrument departure procedures and approach plates will specify a feet per mile. So you need to learn how to convert feet per mile into feet per minute for your given ground speed. So that's kind of why this one's important. Questions so far? No? Good. You guys would tell me if you had questions, right? I hope so. All right, let's really briefly talk about the headwind crosswind table. This is used mostly for landing. So if you are landing on a certain runway and the winds are coming from an angle, it's good to know what your headwind and crosswind components are. For example, if you are landing runway 34 and the winds are at 310 at, let's say, 40 knots, is that going to exceed your crosswind capability? Let's find out. There it is. Bam. So what we do is we look at our crosswind table, which, by the way, your E6B has one on the rectangular side, on the rectangular slide part. Looks like this, but I've got a zoomed in version here. So first we're going to figure out what the angle between our wind and our runway is. If we're landing 3-4 or a heading of 340 and the winds are 310, that's an angular difference of 30 degrees. So we've highlighted our 30-degree line. Then we're going to find the wind speed on one of these arcs. If the winds were at 60 knots, we would be looking at this arc here. In this case, the winds are at 40 knots. So they're here. So at 40 nautical miles, or if your wind speed is 40 knots, your crosswind component is down here on the x-axis. It's 20 knots of direct crosswind. And your headwind component is 35 knots. And you can actually do this using trig. If you guys are nerds like me, you can actually like solve this problem using trigonometry on your exam or in the air. You don't have to, but you know, I think it's kind of neat. But in this case, a crosswind of 20 knots, is that safe? Is that legal? Is it within your pilot operating handbook? You guys should be studying it. You should be able to tell me, is my aircraft capable of a 20 knot direct crosswind? And then you should also go above and beyond that and say, I personally do not want to fly with a 20 knot direct crosswind. It's just not safe. So that's kind of how the headwind crosswind table looks. I probably should have gone over the components. Headwinds on the vertical axis, crosswinds on the horizontal axis. These arcs are your airspeed or your wind speed. And then these lines are the angular difference between your runway and the wind direction. And again, you've got one right here on your E6B. So get familiar with it. Bam. Now let's flip over to the wind side of the E6B. Okay. Now this is actually really cool. What we use this to figure out is if you're trying to go from point A to point B with no wind, you basically just point your nose at it, right? If we go back to our river analogy and you're trying to cross over a river that has a really strong stream, where you point your nose is not the same place that you're going to get to. Like if you point your nose directly across the stream, you're going to end up somewhere downstream. So this wind side of the E6B allows us to figure out exactly what heading we want to fly to get to our destination. It's super cool. I know, I'm a nerd. So they're going to give you your true wind direction, wind velocity, true course, and true airspeed. And we're going to just run through the problem. So first thing we always do is put in our wind. In this case, the true wind is from 240 at 38 knots. So let's go to our true index here. We're going to turn to 240. 240 there. And our wind velocity is 38 knots. Now, if you look here, they don't usually have 0 on the vertical part of the rectangular thingy. So we're going to use 100 as our reference point because it's easy to just say that's 0. We're going to go up to 38 knots. There's 30, 35, 36, 37, 38, and put a pencil mark. You're going to use a real pencil when you take your E6B to the exam. So put a pencil mark there, and then you're going to turn to your true course. So this is the actual heading we want to go to, right? If I want to go from Payne to Jefferson, I want to fly a heading of 300. But this guy here represents the wind. And so we're going to set this pencil mark on our true airspeed, the airspeed that we are going to fly at. 165. Okay? So if you have an airplane here in the middle, this is your nose pointing at 300. This is the wind blowing you off course, right? And this is your ground speed. Your airspeed indicator says, hey, we're flying at 165 knots. But your ground speed, if you were to look at a GPS ground speed, you are only flying at 143 knots. So it's going to take you longer to get there. Also, we're going to count the vertical lines. Here's 5, 10, 11, just about 12 degrees. So to correct for this wind from the left, we're going to put our nose 12 degrees to the left. So 300 minus 12. So that'll be 288 degrees. So we are going to actually put our nose not at 300, but at 288. Did I do that math right? 300 minus 12, 10. Yeah. 288. And that coupled with our wind, I don't know why I'm showing you an airplane when you guys can't see it. That coupled with the wind, so 300, we're going to get blown off course. If we put our nose at 288, the wind is going to help us crab the direction we actually want to fly. Right? I think it's super cool. Then again, I'm a giant nerd, so there's that. Let's do 3 more problems. So wind is 040 at 43 knots. We always do wind first. 040 at 43 knots. We set our 0 mark. 43 or so. True course of 150. Remember, this is the heading we want to fly. This is the direction we want to go in. And a true airspeed of 140 knots. And we put our pencil mark on our airspeed. Just about there. And in this case, we have a tailwind. That's actually going to move us along faster. We're going to be flying almost 10 knots faster than we thought we were. So we'll be at what, 148, 149 knots. So we're going to get there faster than we expected. But we're still going to get blown off course if we don't correct it, if we don't correct for it. This is 5, 10, this is 15, 16, almost 17 degrees, again, to the left. Because while we've got a tailwind helping us along, it's still blowing us off to the right, from left to right. So we're going to correct 150 minus 17 degrees, roughly. So we're going to fly a heading of 133. And that should help us get to where we need to go. The wind is going to push us faster and off course just the right amount so that we end up where we want to go. Let's do one more, or I guess 2 more. 330. Wind is 330. And we always do wind first. 330 at 25 knots. Put our 0 mark, 25 knots. There. Check. Our true course is 020. This is where we want to go. These are all left wind correction. My mistake. Again, I should have better examples. True airspeed of 180 knots. And what's our ground speed? Remember, the grommet here is our ground speed. Grommet, ground speed, G for G. It looks like a ground speed of 163 knots, and a wind correction of 6 degrees to the left. So instead of flying 020, we're going to fly a heading of 014, and that should get us where we need to go. Let's do that last one. And again, if you guys want to follow along, I would recommend it. Wind direction is 110. I went the long way. 110. Wind velocity of 18 knots. That's 118 knots. Our true course, where we actually want to go, of 260 at the top. And a true airspeed of 225. Again, these are all left wind. My mistake. I'll do another one here in a second where you have right wind correction. So 225. Our ground speed is actually going to be faster because we got that tailwind. 240 or 240 knots. And we have a wind correction. This is 5, so 2 degrees. So instead of flying, what do we say, 260, we're going to fly a heading of 258. Cool. So let's say we, instead of wanting to go that direction, we want to fly a heading of 070, same wind, and we want to fly 190 knots airspeed. Our ground speed is going to be 177, and our wind is actually going to be coming from the right. So now we're going to correct 1, 2, 3, maybe 4 degrees to the right. So instead of flying 070, we're going to fly 074. Same concept, except now you're crabbing to the right rather than to the left. It's pretty much the same concept. Does it not make sense? How's that? Give me a shout out if it doesn't make sense. Cool. Let's move on to airspace. We have 13 minutes left.